Okay, great. Okay, so it's 3 o'clock. So let's begin. Okay, so welcome again. Hello, Hafa and aloha to everyone. Thank you for all joining us again today. Welcome to the second webinar in the Pacific Desk 2021 webinar series. I'm David Hitzel. I'm the Pacific Desk Guam instructor. And today's topic of discussion is wave modeling. So just as a reminder for general webinar procedures, first of all, this is being recorded for educational and documentational purposes and will be posted simultaneously on Facebook Live. Please leave questions in the comment section and include your location and affiliation when you do. If you'd rather ask a question verbally, you can do that at the end of the talks. Please refrain from having your video or audio switched on while the speakers are giving their presentations. And lastly, since this is being recorded, I will send out a link to the YouTube recording to all the registrants of the webinar within a couple days. All right. Just a brief advertisement for upcoming webinars. Putting together one related to effective methods for disaster management. And then I also recently attended the International Tropical Islands Water Conference, and that got me thinking that possibly doing one based on hydrology and geography might be useful for our students. So those are topics that are not directly covered by the Pacific Desk material, but they relate to floods and mudslides and water storage, which is very important to a lot of our students. So that'll be in the coming months. Okay, for today's panel, very pleased to present two people that are very knowledgeable in the field of wave modeling. So our first speaker will be Dr. Justin Stopa. He obtained a PhD in ocean and resources engineering from the University of Hawai'i in 2013. He has since worked as a postdoctoral research fellow and a research oceanographer with IFREMER in France, and as a research oceanographer at the University of New Hampshire. He's currently an assistant professor at the University of Hawai'i in the Department of Ocean and Resources Engineering. His expertise lies in wave science and remote sensing, and he has worked on a range of engineering and research projects associated with wave renewable energy, wave climate, operational satellites, and marine hazards. Dr. Stopa also developed the automated wave modeling system with Dr. Fai Chung for the Hawaii Islands Ocean Observing System, and has produced many global wave hindcasts used for climate science and engineering applications. He has also developed new algorithms to extract geophysical parameters from satellite observations. Our second speaker today is Dr. Ning Li. She obtained her PhD in coastal engineering from Tianjin University in China in 2009. And then she went on to become a postdoctoral research fellow in the Department of Ocean and Resources Engineering at the University of Hawai'i. Since 2014, she has been working as the Ocean Wave Model System Specialist in support of PacIOOS and the US Navy's Wave Energy Test Site in Hawaii. And she maintains the daily model forecast for Hawaii, Guam, the CNMI, and American Samoa. Her expertise is in numerical modeling of wind waves, swells, storm surge, and coastal inundation. And her interests include coastal hazards, ocean wave climate, wave energy, and climate change adaptation. Dr. Li participated in the development of a comprehensive wave modeling system and implemented it in the production of a 38-year high-resolution wave climate hindcast for the Hawaiian Islands, which is widely used in wave energy resource characterization, renewable energy development, coastal hazard mitigation, and infrastructure design, as well as coral reef ecosystem assessment. Okay, so I don't want to go over too much in terms of our training for marine forecasting in the Pacific Desk, because if you want, you can go back and look on our website and look up the link for the surf forecasting, and that includes kind of a breakdown of what we do there. But this webinar, actually, I thought it would be a good idea when we did the surf forecasting webinar to do something that was more specific on the wave models, because it's a whole science in itself. So for Pacific desks, the WAVEWATCH III is basically our go-to tool for marine predictions in the South Pacific and Micronesia, and that is because it's very economical. So taking observations of waves in the ocean is expensive. The initial tool, the devices to measure things is expensive, but also, especially in the case of buoys, they're at the mercy of all the forces out there in the ocean, and they get lost, they go adrift, they get damaged, they have to be replaced. So the WAVEWATCH III is a very economical tool, and it gives us information over the entire ocean basin, or over the ocean basins of all the globe. Of course, the observations are important, yet again, though, to do verification, make sure those model runs are correct. Okay, so the purpose of this webinar was to, in the training, we convey the idea that there's certain biases, there's certain strengths and weaknesses to them, but I think those might be understood better if everybody understood a little bit about the guts of the model, how it works, what sort of theories it's based on, what sort of math, not too technical, but some of the mathematics that goes into that. So that's why I brought these speakers together today. And then from there, to explain that there's various types of wave models. There's the one we use most frequently, the WAVEWATCH III, but there's also certain situations where a sort of high resolution wave model is more applicable. So those would be situations where you're near shore, where you're influenced by topography, you're influenced by the bathymetry. I'm sure Justin will explain that waves behave differently depending how deep the water is that they're in. And then one of the other topics I'm hoping somebody will go into is the influence of currents. So that I titled this slide, "Hey, where did that swell go?" So there's some theories out there that swells can be heavily influenced by currents and redirected, diminished. So I'm personally curious about that. Okay, so we're here to understand some of the theory upon which the WAVEWATCH III and SWAN models are built. And based on understanding those better, then we can decide better how to make use of the strengths and weaknesses of each type of model, how to appropriately apply them for marine forecasting, and how to understand how we can use the model biases to our advantage. All right, and with that, I will pass it on to our first speaker. Professor Stopa, are you ready?
Yes.
Okay.
Once you stop sharing, I can share my screen.
Okay.
Okay, so this is the first part of the presentation today, and the focus here is really to talk about deep water wave evolution and spectral wave models. So most of this is really a summary behind the guts of how these spectral wave models work. And in particular, this is applicable for both WAVEWATCH III, which is widely used, SWAN, and the other model is WAM, which is still used quite a lot in Europe, but less so elsewhere. And really, this presentation is meant to complement what Ning will describe next, which is more about the applications. So here's an outline of the presentation today. I'll give a quick introduction of spectral wave models, and then I'll get into the guts of the presentation, which is about deep water wave evolution, and I'll talk about the three dominant terms, which I will call source terms, but they're also sink terms, meaning it can add or subtract into the wave equation. So there's three main terms, and the first one is input, the second one is wave-wave interaction, and the third one is dissipation. And then I'll give a quick summary then about the balance of these terms, because that's actually very important in this wave model. And finally, I'll summarize everything with just one slide. So just to introduce, and this was a nice introduction from David, just briefly about different wave sources that we have. So buoys, but really we could call this in situ observations. And these are great. We get a full wave spectrum, but we're limited, and we're limited in spatial coverage. But we do have high temporal information. And just to introduce, if you're not familiar with the wave spectrum, a wave spectrum, this plot on the bottom here shows a wave spectrum from north of Hawaii here. And the first plot here in the black shows frequency versus energy. And we can see that there's three different swells. And then if you look in the directional sense, so this is the color represents energy, and the direction is in the polar plot here, and then the distance from the center represents the wavelength or wave frequency. We can see that they're all coming from different directions as well. So really what we're after typically is a wave spectrum, because that gives us all the detailed information about the sea state environment. The next source of information we have are satellites. Satellites are great because they cover large expanses of the ocean, but we're often limited because it's difficult to estimate spectra from these type of technologies from space. We can do it, and there's been advancements, but it's still difficult. And finally, models, which is our topic today. And these are great because we can estimate spectra anywhere in the world. We can also forecast future events, and we can also hindcast. So they're very universal. So I'd like to point out that the reason that we use spectral wave models typically in deep water is because the properties of the wave spectrum evolve much slower than an individual wave. And this, what I mean is that an individual wave, if we have to actually propagate the crest at a certain direction and certain wavelength, that evolves at a much higher rate than actually the integrated energy. So this is a much more economical model to use for deep water wave evolution. So really, this is the workhorse behind all of our wave forecasts and all of our wave hindcasts. And I see that these models are probably going to be around for a while, probably about even 10 years into the future. I still think we're going to be using these type of models. And obviously, there's a lot of different applications, from navigation, engineering, design, even scientific interests like air-sea exchanges, climate, and of course, my favorite, recreation. So these models have all different types of applications, and Ning will go into more of those. So just to introduce, this is the governing equation of the model. And I'll go through this pretty carefully here. So E is our wave action, or our wave spectrum. And this is written in terms of a wave number, because I thought it was a little bit easier. And on the left-hand side of the equation here, we see that we have the change in time. We also have this del operator here, which is the change in space. And this is the group velocity here. So it's the change in space. And then also the change in spectral space. So how the energy moves within the wave spectrum itself. So on this left-hand side of the equation, you can see that this is a conservation. This is like a total derivative, meaning that the energy is just moved around. So how do we get energy into this equation? Well, that comes from the right-hand side of the equation. And this is where I wrote the three main terms that we're going to discuss today, which is the input, in other words, the growth, how wave is actually transported in spectral space and how it moves around through the wave-wave interaction, and then finally dissipation, how waves break. So this is a quick summary statement then, or a take-home message that really encompasses the whole presentation today, which is that ocean waves are generated by wind. This is our input term. They lose most of their energy through turbulence as they break. This is our dissipation term. And finally, energy is also shifted in frequency, and this is the nonlinear interactions term. So that's our wave-wave interaction. So let's now begin with our first term, our input term. So this was originally formulated by Miles, and this was a paper, I believe, in 1957. And what Miles said was that there's a pressure differential that has to develop on either side of the crest. So this means that in the schematic here, there would be a high pressure on this side that's called the windward side, and then there's a low pressure on the leeward side. And this pressure differential, what it will do is it will start pumping, it will, in other words, start pushing on the windward side and will start pulling on the leeward side. And you can see that as the waves get larger, that this pressure differential also becomes larger. So this is a really an effective way to grow waves. And this is what we call a positive feedback loop. So what Miles did then was he formulated the process like this. He says the input term is equal to, this is the angular frequency times our beta term, which is times our wave energy. And here beta is proportional to this term here, which is U divided by C squared. And we also have a cosine of the wave direction theta minus the wind direction theta wind. And what is important here is that we have U over C squared. In this functional form, this parabola has really stood the test of time, and this still shows up in the models that we use today. And there's also been a number of observations that support the use of this functional form. So I'd like to point out that in this theory from Miles, the wind is decoupled from the waves. And what I mean is that the waves themselves do not affect the wind, but you can see that in the schematic even, you can see that these streamlines from the wind are actually distorted by the ocean surface. So next, let's look at some observations. These are a little bit dated, but I do think this was more of a seminal work on the topic. This x-axis here is U star divided by C, and U star here is our friction velocity, so really close to the surface, but not right on the surface, the wind speed. And then our y-axis here is our growth term, our beta term. So you can see that there's a relationship as the wind gets larger, so does the growth into the ocean. And this, note that this is on a log-log scale. So there's two different lines on this. The first one is from Plant, and this is the dash line. So he used all the markers here that are not filled in, just have the outline. And then there's another study from Schneider in 81, and he showed these are the dark filled in markers here. And both of these studies came up with a fit to these data. And note that both of them, Plant and Schneider, both have the same functional form that Miles did of U star divided by C squared. And also note that we still have that cosine relative direction of the wind to the wave still in the equation. So that's just more evidence suggesting that that functional form holds. So the next major advancement, in my opinion, is from Peter Janssen in 1991. And so first, an assumption that we make is that the winds have a logarithmic profile, and that's given by this top equation here. And this is very similar to what we see in fluid mechanics, like law of the wall type idea. And it's important here to note that we have U star over kappa. Kappa here is the von Karman constant. And then we have this Z naught term. And this Z naught is difficult to define often. This is a roughness of the surface. In this case, this is a roughness of the waves. Meant, from the perspective that we're in the atmosphere. So typically, and there's been many studies that have actually used Z naught as a function of a Charnock parameter. That's given by this next equation here. And typically, this has a value of 0.015. And there's actually a number of studies that formulate this Charnock parameter as a function of waves. And they actually, it's proportional to wave age. So what Peter Janssen did, and this is written out in this long equation here, so don't be too scared about this. Let's just focus on the key components here, which is that we still have U star over C squared. So in other words, we still have that original Miles formulation embedded in this equation. We also have this cosine of u minus u naught, so the relative direction of the wind to the waves. And then how his major contribution really is in this term, big Z to the fourth power. And if you follow this equation, Z is given by this equation here. We have log of K times Z1. Z1 is really meant to represent a roughness here, a roughness of the waves. And that's given by this equation here on the bottom, which shows that this Z1 is a function of the wave stress divided by the wind stress. So this is a way that actually the waves modify the profile of the wind speeds. So now this is what we would call a two-way coupling, meaning that the waves influence actually the atmosphere. And this was, I think, a major advancement because it made the model work closer to what we observe in the ocean. And it did this more through, I don't want to say physics because these are parameterizations of the physical process, but the physical behavior of the data simulates more closely what we see in nature. So the next advancement, I'd say, in this line of research came more recently in 2010, and this was from Arjuan et al. And what Arjuan did was he built on Peter Jansen's formulation. And what he did, his addition, was he said that U star, or friction velocity, should be written this way. And really, it's the addition of this term right here, which was the major contribution. And what Arjuan was trying to replicate here is, I'll just go back a few slides to demonstrate this, is he is trying to replicate the sheltering of the wind on the leeward side of the crest. So I'll go back to the original schematic here. So as the wind is going over the crest, there's actually going to be a separation point, probably in this area, just below the crest. And this can actually mean that this part of the waves interacting with the atmosphere is not receiving the same amount of momentum as, say, the windward side does. So this is a little bit of a sheltering effect. And as waves gets bigger, then this sheltering effect will be more prominent. And I think that I would put this on a list of major advancements on the description of the input term, because this was then a way that the model would basically cap itself. So there's several notable papers that show that there's a saturation point that is reached in really extreme storms. The one that comes to mind is Powell, which was actually published in Nature. And Powell showed within tropical cyclone forcing that at some point, the ocean is not able to receive momentum and energy from the atmosphere, or it really reduces quite a bit. And that's due to the fact that you have a lot of sea foam on the surface, and there's not as much friction between the atmosphere and the ocean. So energy really slows down of being transferred into the ocean. So this term really is a way that we can parameterize that. So the addition of this term enabled there to be a cap in the model that comes out of this equation rather than just putting a hard line, because before that there was just a split function here that said a min or max. And if you look back at the Jansen formulation, there was some min function there that you just take the minimum of a constant versus the term. And the other way that I can demonstrate quickly of how the impact of this term is in this bottom plot. So this bottom plot here shows the mean squared slope, which is k squared times our wave energy. And k squared, this is actually proportional to a fourth order moment. So this means that there's going to be more weight on the high frequency components of the spectrum. So this is just some wave parameter of the sea state. And then on the bottom axis here, we have the wind speed. And then the colors represent different wave heights. So you can see, I'll draw your attention to the upper right panel here. And these are actual observations from a buoy. And it shows that as the wind speed increases, so does the mean squared slope. It also shows, say we have a fixed wind speed, And as the waves increase, the wave heights increase, there's also an increase in mean square slope. So this is what we want the models to behave like. So this is actually our truth. This is our ground truth from observations. And then these 4 panels here show different model formulations, actually of all these source terms, but they all have different input terms. So the first one here, ST2, shows that, well, there's certainly a gradient in the wave heights, but the magnitudes are quite different from our observations. So this means that this model is not able to capture the high frequency part of the spectrum correctly. The next model here, ST3, this is actually very equivalent to WAM, the original WAM 3 and even WAM 4 source terms. And you can see in this case, the magnitudes are a little bit better, maybe a little bit of overestimation here, but the gradient in waves is not in agreement with the observations. We see that at some point, the highest waves are not the highest, meaning that a mean square slope is going to be higher at a lower wave condition, which again is not physical. Next, we have ST4, which we can see that the magnitudes and the gradient are well matched, and even the range of them also match pretty well. So this was the formulation by Arduin, and this is one of the reasons I think that the addition of this term, why we have such a great match here. And the last one here is from Australian researchers, ST4. And you can see that the magnitude here is good. The range of color is good, but the gradient of color is good, but the range here is actually a little bit different than the observations. So overall, I would say that I would give the slight nod to this formulation that matches the observations the best. Okay, so now let's transfer into our next source term, which is wave-wave interaction. And this is a difficult term, I guess, at least to describe in this context in a very short time, but I'll do my best here. So waves are in the ocean, are not linear, therefore resonance exists. And in deep water, there's a resonance condition that says that when 4 waves, written mathematically this way, so we can think about it in terms of wave frequency or in wave number. So if we say wave number K1 plus K2 is equal to the wave number of K3 plus K4, then we say that there is a resonance condition. So I'll briefly describe what this is through the schematic on the bottom. So say we have a wave tank here, and we can have a wave maker 1 and wave maker 2 that produce waves with a certain direction and certain wavelength. So these waves interact, and then just through superposition, linear superposition, we would see a diamond pattern that would form. So the dark circles here would represent the peaks of the waves adding together. And then in these areas here, there would be the water surface elevation would be reduced. So this is where the troughs of the combined waves. So this is diamond pattern A. And now let's say on the other side of the basin, we would have another set of wave makers. And these wave makers can create different wavelengths in different directions. And what we create is another diamond pattern. So resonance occurs when the diamond pattern, so the resultant wavelength of the diamond pattern drawn by these straight horizontal lines here, when these match between diamond pattern A and diamond pattern B, this is a resonant condition. So when this occurs, what happens is that the wave energy is changed between all different wave components. Mathematically, we could use this kind of picture, meaning that the hypotenuse of each of these triangles of diamond pattern A and diamond pattern B, when they match, this is our resonant condition. So you can see that in the ocean, if you have a continuous distribution of wavelengths, there's an infinite number of possibilities that we can have that meet this wave resonance condition. So this was formulated originally by Hasselmann. This was a series of papers. 1960 was the first, 62, 68, and then there's maybe it's a Hasselmann et al. In 85 that really formulates an analytical solution to this problem. So this equation here is written in terms of K4, so just one wave number. And there's two terms here. This first term, you can see that there's actually no K4. Well, K1 plus K2 minus K4, this is actually K3. So this term is passive in terms of wave number 4. And then this other term here actually has a K4 in it. And this is an active term. And notice that the sign here is positive and minus. This means that for the energy in K4, the energy can be can grow or it can decrease. So this term can be positive or minus. And that's the important part. That's the only thing I wanted to really demonstrate from this equation. And actually, these functions, T1 and T2, are really ugly equations. They would probably fill up a whole slide here. This is actually a very expensive computation. So solving this fourth order integral takes a lot of computational power. Even with our advancements in computing, we can still not run a global model using the full solution. I have seen a couple studies, I don't know if they've been published yet, but I have seen a couple folks that have been doing regional models that actually have this full nonlinear term accounted for. So what we do in practice then is we use what we call a discrete interaction approximation, or the DIA. And this was formulated by Hasselman in '85. And this is an approximation to this full analytical solution, which he gave in 1960. And this is tuned for deep water wave evolution. And I like to point out that it's supposed to work well for deep water. However, the spectral shape is not too accurate. And actually, the wave spectral shape ends up being a little bit too broad. So next, I'd like to just describe how this term works. This was from a paper from Young and Van Letter in 1993. And this is a one-dimensional model, so we can just one space. It's really just to understand the theory, and it has the full nonlinear term modeled in this. And we input this spectrum here. So we just make a sharp spike in the spectrum at 0.4 hertz. And then over time, this is only 3 minutes later, and you can see that this discrete spike that we have here is reduced. And if you look at the source terms, this is a breakdown of actually all three source terms. You can draw your attention to this solid line here, which shows that it's really behaving closely at this spike. So this nonlinear term, what it does is it will reduce these spikes, and it ends up making a very smooth spectrum. And that's just how it behaves. So this is one of the reasons why we have spectrum that always have very similar shapes, at least in the high frequency component of the spectrum. And this has been referred to as cell similarity. So now let's move into our last source term, which is dissipation. And this is the conversion of mechanical energy into turbulence. And this goes into the air and water. And specifically what I'm talking about is wave breaking. And this is really the white capping that occurs in the deep ocean. There's also depth-induced wave breaking, but here I'm specifically referring to wave breaking in open ocean. So in 1944, Mitch came up with the idea that the wave orbital velocity cannot exceed the celerity. So mathematically, we would say U has to be less than or equal to the celerity of the wave. This means a particle cannot fly off the ocean surface. And if it does that, the wave will break. And he came up with, just using linear wave theory, that our maximum steepness is 14%. So H over L here is 0.14. And that's just an upper limit. So that really doesn't help us much in modeling, because waves in the ocean never hit that limit. They actually break way before this 14% limit. Breaking usually occurs near the crest, and this is just a schematic from a laboratory experiments, which shows the white capping right at the crest, and it's actually moving more centered on the leeward side of the wave compared to the windward side. And there is some implications of that. Actually, there's been some theories or formulations that basically try to mimic what Miles did in the ocean side, and say that this pressure differential of the added braking is basically the flip of the input on the ocean side. And that's one way to model it. So the reality is that this term is very difficult to describe from theory. There's still not a consistent theory that will describe breaking. So pretty much the way we treat it in these spectral wave models is to use a stochastic approach, or we use probabilities to describe wave breaking. And my own opinion on this topic is that we are a little bit limited by our observations still. And as our observations increase, then we will have a better understanding of this term. And this is difficult because there's an importance of scales here. In other words, we need to resolve both long waves and short waves, long waves meaning, say, 500-meter long wavelengths. And we also have to resolve the short scale waves, say on the order of meters, simultaneously. And I think there will be advancements in the future with stereo video cameras, for example. As their field of view gets larger, we will be able to make more high quality observations of wave breaking. So this is just one way we can do it. This is the dissipation total, and this is how we treat a stochastic process in our wave model. So we need our dissipation, which is our epsilon. We also need a weight function, which is a function of wave height and period. And then we also need the probability. So probabilities we typically get from just observing the surface of the the ocean, and then counting the number of whitecaps, and that gives us some probability of the waves breaking over that surface. So this is pretty much how we calibrate our P. And then we also have to get some weight of that, and that becomes from more high resolution observations. I believe there's many seminal studies from FLIP, from Scripps, which get us closer to a weight function. And I also like to point out the other schematic here shows that whitecapping increases as a function of wind speed. So in other words, as wind speed increases, that's the x-axis here, we have the number of waves, or this is the probability of breakers increase. And the other thing I like to add from observations is that we have the total number of, this is steepness on the x-axis, and then this is a probability of the steepness. And we can see that the total wave environment is given as just this line here. And you can see that this follows a Rayleigh distribution more or less. And then the steepness of the individual breaking waves actually is very similar. It's still a Rayleigh distribution, but a lot reduced in quantity here. So those two pieces of information helped us formulate how we can define these breaking probabilities. That's why I added these two plots here. So this is just a hand waving description of how this is actually included into the model. And the major seminal study, which we still use, is from Phillips in 1985, who came up with the idea of a breaking spectrum, which we have to define. And this is really our epsilon function, basically, in the previous slides. This is our breaking dissipation rate. And note that with this formulation, we have to define these breaking probabilities for very small increments of our wave spectrum. And that is what is difficult. In other words, we really need high resolution information in wave number as well as direction, which usually we don't have from observations. So to put this in the scope, this was a really nice paper here from Banner et al. And he used these very coarse requirements of a d theta of pi, and then also a decay of 0.6, the peak wave number. So we didn't have very high resolution he couldn't really resolve from his observations high resolution information about the breaking spectrum. So the approach is, first we have to define this B, and this is pretty much done with some kind of observations that we have. And then what we do is we attribute a breaking probability for each wave, and then we transform that into our spectral model from the previous equation on the previous slide. And here is just one formulation. This is from the Arduin formulation. And note here, I just wanted to give one functional form that we have a k cubed here. So this means that there's higher weight on the high frequencies. And wave breaking does in general occur pretty much at the peak of the spectrum, and then higher frequencies from that almost continuously. So one final note then about all these terms is that if you notice in all these equations, there's always these empirical parameters that need some tuning. So this will lead into the next section, which is the balance of these terms. So I'd like to start by saying, so let's go back to our, governing equation here. And note that I like sharing this example. I would say maybe 20, 15 years ago, we were overestimating our input term and we were underestimating our dissipation term. And that's actually okay because our model still was behaving all right, because we can never constrain the models well. And that's because that our observations, what we can measure from the ocean environment from buoys really well is the overall spectrum. So that's the integrated spectrum. But what we can't do is isolate very specifically, in particular on the dissipation term. Our input term, there, we've had better experiments to basically isolate that term. So I just wanted to mention that because we can have a model that works pretty well, but we could be orders of magnitude off because there's a lot of fudge factors in here between all these different terms. In other words, how we calibrate them. So this is an example model run, which just has an infinitely long fetch, and it has a constant wind speed of 15 meters per second. So the top panel here shows the three different terms and the spectrum that's given E as the dark one. And then we can see the breakdown of these three terms. So our input term here is in pluses. So that's our blue term. So you can see that it's only adding energy into our spectrum. It's on the positive side of the axis here. And then our dissipation term more or less mirrors the input term. So it's in the gold color here. And then look at our nonlinear term, which is our, sorry, that is the green term here. And you can see that it's both positive and minus. And more or less, we always see that the nonlinear term has a little bit of a positivity on the lower frequencies. And that actually, even though it's a really small amount in this case, look at the green line, just a little bit larger than the black line, that little bit matters because the energy then transformed. This is the only term that will add energy into lower frequencies. And why is that important? Well, once the energy gets into lower frequencies, it persists in the spectra for long periods of time. And this is one of the reasons why swells decay at very low rates. And that means that energy in the spectrum in these low frequencies stay there. So now after a much longer time, so this is after 48 hours, this was after 3 hours, we can see the evolution of these terms. So you can still see that the input more or less mirrors the dissipation, and we still have basically the same shape of the nonlinear term. In our spectrum, you can see that it transformed with a peak of, say, 0.25 hertz down to, it looks like less than 0.1 hertz. So really, I want to stress that the balance of these terms is important. And I wanted to describe the overall shapes of these terms. So this is a final summary slide then of the three different terms. Our input mainly occurs just less than our peak of our spectrum. So that's given by this big arrow here. The dissipation term actually occurs most strongly at the peak of our spectrum, but there's also energy being removed from higher frequencies all the way down into the tail. Our nonlinear term transforms the energy both in the positive direction and negative to lower frequencies and higher frequencies of the peak. And in general, mid frequencies typically lose energy. That's because of our white capping term. So this is really a summary of these three terms and how they behave with our wave spectrum. So then here's just a quick summary. I'll just quickly go through here. Our input term really defined by miles is proportional to U over C squared. And there's been the two major advancements from Peter Jansen and then Arduin. The nonlinear terms, which is described by Hasselman in a series of papers. This is a full solution, but it's very difficult, very expensive for us to resolve. So we make an approximation. And then finally, our dissipation, which is difficult to define due to our lack of observations. And this is really treated through the spectral wave model through probabilities. And this is highly empirical term. So if you want to study something, or probably dissipation term needs the most work. And finally, I'd just like to emphasize again that the balance of these terms is important for the overall accuracy of the model. So I guess now we can transition into Ning's talk about applications.
Yeah, why don't we do that? Why don't we go directly to Ning, and then we'll do
Okay.
questions.
Thank you, Justin. That's a great presentation. And I think Justin laid a very solid foundation for our audience to understand how the model works. Now we have very accurate model we need to implement in our operation to use the model as a tool to provide useful information for the public audience. And I give this presentation, but that's definitely a teamwork. And Justin is one of the people who developed this wave modeling system. And later on, I joined the course, and the entire modeling system also supported by the research computer facility team, the PacIOOS data management team, and to manage the data and put all the information online. And also our colleagues, Dr. Chen from meteorology department provide wind forcing for us. So this is definitely seamless teamwork for this model to be put into operation. So I want to acknowledge that first. Now let's start my presentation. Okay, so I will start with a very complex wave climate around the Pacific Islands, and then the buoys who measure the wave conditions, and then the wave model system, and it's her implication for forecasting and handcasting. At the end, I will talk about our future works. Okay, so Pacific Islands at the middle of the ocean can receive waves from various directions from the local and the distant sources. Hawaii is a good illustration. Like for example, we receive waves from northwest to north generated by extratropicals in the North Pacific, usually near Kurile and Aleutian Islands, usually happen in the winter time. And we also have south swells, which was generated from the south hemisphere, usually stronger in the summertime. And we also have year-round trade wind, usually coming from the northeast to east. And we also have, in the storm season, we have storm waves from very different directions. And also for the like passing by subtropical cyclones and the cold front also can generate a strong wind to bring big waves to the islands. For other Pacific islands, the wave conditions can be similar or slightly different, and they may have their very complex wave condition too. To capture, to measure the wave conditions, the Pacific Island Ocean Observing System, with acronym PacIOOS, have deployed 15 wave buoys around Hawaii, Marshall Island, Guam, and American Samoa. These wave buoys provide very valuable data. They flew with the free ocean surface to continuously record the horizontal and vertical displacement. And based on that, we can compute the wave parameters, like in half-hour intervals. Those wave parameters, I think most of you guys are very familiar with, like significant wave height, peak period, peak direction, average period, and so forth. And based on the surface displacement, we can also derive the wave spectrum in 1D or 2D in 30 minutes intervals. And from Justin's presentation, you should already have an idea how important the wave spectrum is, and it contains full wealth of information about the wave conditions. And based on long-term record of the wave conditions, we can get some useful statistics, like for example, the minimum, maximum of wave height, and the joint distribution, or the occurrence level, basically the return period. And we can also to get some useful features of those wave conditions through the phasor plot, wave rose plot, and the period rose plot. For who are not familiar with those informations, I will refer you to the Coastal Data Information Program, their website. It basically includes all the buoys around the Pacific, and you can just look around and see all those informations. It is public available. And the wave data are quite useful, but it's very expensive, like David mentioned. And also it's not enough because the ocean water are huge, and we only have just those like 16 buoys. It cannot fully describe what's the wave conditions around the island or in a large scale of spatial area. So we want to know, we want to have a bigger picture of what's going on in the ocean. Now the wave model can fill the gap, play a role to complement the buoy data to give us a big picture of the wave conditions. So Justin already gave a foundation like how the wave model works, from the wind as input and the nonlinear interaction between individual waves, and also the breaking as dissipation. So the good wave model, especially the spectral wave model, can able to resolve the wave conditions quite well. So we assemble the spectral wave model, like for example, WAVEWATCH III and the SWAN, and based on the accurate bathymetry data and the shoreline information, sea ice information, and also with the wind forcing from global and the regional scale, that will allow the model to be able to produce the wave conditions in the spatial and temporal scales very well. So we the whole team develop the wave model system, and we implement the wave model system to provide operational wave forecast. This slide shows you how the flow chart of the forecast system. We have wind forecast from NOAA NCEP in the half-degree resolution, and we also downscale, like Dr. Chen's team downscale the global wind forecast into our regional domain to provide a higher resolution to resolve how the wind are impacted by the mountains, channels, and these global and the regional wind together as input to forcing our global WAVEWATCH III, Hawaii regional WAVEWATCH III, and also it provide a boundary condition for the island scale and the even higher scale SWAN wave model for some strategic locations. For example, we have wave engine test site on the windward side of Oahu. So we have a higher resolution there too. So, so with this implementation, we are able to produce daily the wave forecast, and each set of forecast will include 7 days of wave prediction. And you are able to go to PacIOOS website. I put the link there to get the forecast information at each locations or for every domain. And we use the buoy data to compare with our forecast for quality control. So you're able to have an idea how good the forecast is. And the forecast has a wide range of applications. It's for, you can use it for recreational purpose, or you can also use it for engineering application. Like for example, you want to go to the ocean to get the buoy or to fix something, you have to know, you have to find a good weather conditions to go there just for safety purpose. Here is a demonstration. At the wave energy test site, there is a task need to replace and repair the anchor, which is located at the bottom of the ocean, and it involves a big ship, include crane, include ROV, include multiple peoples from different organizations. This is a big operation. For the equipment and the personnel transfer purpose, they want to have wave conditions usually under 4 feet, because if the conditions are too rough, then it will be too dangerous to work at the sea. So we have been waiting and looking forward the weather windows. And on our forecast issued on October 26, 2019, we already see a decreasing trend of the wave height at the site, starting from November 1st. And 2 days later, the forecast continue evolve, and the decreasing trend was confirmed, and we see a 3-day window. So we inform the team, and they get ready, they prepared, and the operation was safely conducted from November 1st to November 4th. Within this 3 days period, those pictures shows the whole crew, and they pull out the anchor, and then later on how they take out and bring the anchor back to the sea bottom. So you can see the wave condition are quite well, so they are able to finish this whole operation very smoothly and safely. So this is just one example. And like another example, this is just a fresh example, is we always want to retrieve there is a float there at the wave energy test site. We have been waiting for the weather to come down for a while. And last week from the forecast plot, we already saw there is 1-day window with significant wave height under 4 feet. So last week we already tell the team, and then today, April 20th, this morning, the sea engineering, the whole crew with their ship, I remember it's Kupa'a, they go there and very quickly remove the float and tow it on shore. So this is the picture from the camera. You can see the site. We have some wind waves there, but overall the wave conditions are pretty good. So they are able to go there and to get the work done pretty smoothly. So this is just a couple examples how people use the wave information for their engineering purpose, for their work, and so forth. And when you go to the PacIOOS website, you will notice that for the forecast plot, the solid line is basically the bulk parameter, which is a significant wave height. And you have also saw a lot of color lines. This is partition of forecast, which shows how many wave components how many wave components are happening. Like for example, right now, if you focus on the red dot, that's like a swell at the end of the swell from north, and the decreasing basically shows the swell are fading away, and the blue dot is from east, and with period of 8 to 10. That's from trade wind waves, and it's in the range of about 3 feet. So basically with this forecast, you are not just get the overall wave height, you can also look into it to see where, how many wave components contribute to the overall wave conditions. Like for example, you are a surfer, you definitely want to surf under the swell conditions. Then you can go to the forecast plot and then see if there is a swell coming, if it's good, big enough for you to surf. So so the forecast has been widely used to, besides to okay, next slides. So people often ask, like you listen to the weather forecast every day. So you ask how good the weather forecast is. The same thing when you look at the wave forecast, you will have a question like how overall, how good, what's the uncertainty level of this wave forecast? Yes, I showed two demonstrations, like people use this forecast for their work, but how generally the forecast, what's the bias or the uncertainty level? So we did some investigation because each day we have 7 days of forecast, and so we divide each forecast data set into 7 segments with lead time from 1 to 7 days. And then we concatenate each segment into a continuous data set. And then we compare with the buoy measurement for a long period of time. So we will have a general idea, like as the lead time increase, how the forecast quality will change. So the left panel is the scatter plot. The x axis is the measurement, and the y shows the forecast. As those scatter more close to the perfect line, that means the measurement and the forecast are more close to each other. That means the model works the better. And when the spreading increase, that means the uncertainty level also increased. As we can see from the first day to the 3rd day, the forecast has been maintained at a pretty good level, and the root mean square error compared with the buoy measurement was within 1 feet, and the correlation coefficient is around 0.9. But as the lead time increase, like more into the future, the spreading increase and the root mean square also slightly increase, and the correlation decrease. That means the forecast, the overall, the quality start deteriorate. It's just like our weather forecast, like it may be pretty accurate tomorrow there is going to rain or not, but 1 week later the uncertainty is larger. And the right panel shows the overall quantile plot. So basically within the 7 days, most of the forecast are within 10% of the buoy measurement, except on the 7 days forecast for the big extreme event. So within that, we would conclude that the forecast can provide very reliable wave conditions for 4 days. From the 5th day to 7th day, you can use it as a quantitative information, qualitative information to provide reference for your work, for your future work at the sea or your plans. So the forecast is quite useful, but for example, with climate study or with energy resource assessment or infrastructure design, they would like to have a longer period of wave information for their research or for their engineering project. So this short-term forecast will, it's not enough. So I forgot this. We also have operational wave forecast for other locations. Like for example, Mariana Island, we also have a higher resolution SWAN forecast for Saipan, Tienan, Rota, Guam, and also 100-meter resolution for Upper Harbor, and also in the South Hemisphere, Samoa, and the American Samoa, Tutu'i Island, and the Manu Islands too. So I would encourage you to go to PacIOOS website to look around and see the available forecast data. The left panel shows the forecast plot around the CNMI. So in last week, Friday, the wave condition at Guam is about 6-7 significant wave height, 6-7 feet, and the buoy measurement shows basically it follows the buoy measurement quite well. And from the forecast plot, we also notice there is a big increase in on April 19, that's yesterday. And when usually this kind of plot should happen, then I will go to the wave data and see what's going on. And it turned out the forecast plot already revealed the influence from the tropical storm Sergio. Even so, it turned out the Sergio is more for the Philippines, more closer to the Philippine side, more farther away from the Guam side. But we are able to see the influence from the storm 5 days ahead of time, because the waves generated by the storm can propagate towards Guam through a long distance. So this is just one another example how the forecast can provide useful information for the hazard warning or for the daily use. And earlier we talked about people need a longer period of wave information for the climate study, for resource and characterization, for the infrastructure design. So we implement the forecast system for long-term wave handcasting. We use the long-term climate forecast system reanalyze wind forcing in the global scale and downscale it into the regional scale for Hawaii, and use the wind forcing as the input to force the wave model to produce this long-term handcast data. And the handcast data was validated with all available satellite and bush measurement. And it provides a good description of the wave climate and the wave conditions in around Hawaii area. The top plot shows example the comparison of handcast and the buoy measurement in the entire year of 2016. As you can see, the handcast are able to reproduce the seasonal variation pretty well, and also the rapid change of wave conditions in hourly scales. But except there is missing some of those peaks for a big event. So, but overall, the handcasts are able to provide a good descriptions of the wave conditions. So we can use this database for a lot of applications. And one of application is, like, for example, you want to build a breakwater or to mooring system in the middle of the ocean. You want to know what's the probability distribution of the wave conditions. Basically, what's the 20-year or 50-year or 100-year return period wave height. So you are able to, based on your risk level, to design your equipment accordingly. So we know Hawaii or other Pacific islands, we have very various kind of wave conditions, from short period wind waves to long period swells. And those different wave conditions, they have totally different recurring probabilities. So we have to separate them for different, we have to analyze them separately instead of group them all together for one probability analysis. So we divided the different wave conditions into 3 groups, like a wind cease group with basically by peak period less than 10 seconds, or swells with peak period longer than 14 seconds. And then the other group is the waves in the middle. And then we pick the maximum wave height from each year for each group and use this 30, 40 years maximum wave height to populate the extreme value distribution. So through this extreme value distribution, then we are able to extrapolate to get, like, for example, 20 years return period, or even 100 years return period at different locations. So you can use this information as a basis for your engineering design. So, like, for example, this at the right plot shows the extreme distribution for wind cease, swells, and the moderate period waves. They are 20 years and 100 year marked by the yellow dot and the red dot at different bursts of the wave energy test site. That information sounds good and useful, but we lack one component from this handcast data set. That's storm waves. So in the past few years, I think we all have a feeling that it seems there is more and more storm are coming, or it get more closer to the island. So if you still remember last year, we have Hurricane Douglas, which get pretty close to our Oahu. And then in 2018, we have Hurricane Lane, which almost make a landfall at our island. And then further in 2015, on the same day, August 30, there is 3 hurricanes spanning in the Central Pacific at the same time. So it sounds quite scary. So given to that, we have to pay attention to the hurricane wave conditions. But over the last 50 years, majority of the hurricane is passing from the island from the south instead of directly hit or get pretty close to the island. Based on that, we do not have enough historical record for the hurricane wave studies. So to solve this problem, we collaborate with the Professor Emmanuel. He's from MIT, very established professor on climate modeling. And we use a global climate model, which is forced by the historical or the project greenhouse gas concentration, are able to provide pretty accurate synop weather conditions, which will provide a basis for the hurricane simulation. So we asked him to help us to do 50 simulation of the hurricane conditions for 1980 to 1999, basically 20 years of period time. That give us equivalent 1,000 years of hurricane simulation, which turn out to be about 2,500 hurricane scenarios. So based on those hurricane scenarios, we can select the most influential one and then do hurricane wave studies. Like in this case, I still use the wave energy test site. I select the hurricanes with category 1 or above strength and the passing within 200 kilometer around the site, and to model the wave conditions, to model the hurricane wave conditions for this about 205 hurricane scenarios. So based on the hurricane track strength and the radius of the maximum wind, we are able to get the wind forcing for the hurricane wave modeling. And for this is the example, just a scenario. Basically the most severe cases when the hurricane make a direct landfall from south of all the island, they're going to generate pretty big waves at the site. So for each of these hurricane scenarios, we pick the maximum significant wave height and the corresponding peak period. So we're able to find from the top panel is a scatter plot of this significant wave height and the peak period. You can see a quite clear breaking line. As the peak period increase, the maximum significant wave height can go pretty high. And from those 250 hurricane scenarios, we are able to get extreme distribution of hurricane wave conditions to get similar 20-year and 100-year return period hurricane wave conditions. So with that, with this handcast database as well as this hurricane wave database, we're able to better provide the extreme wave conditions for around the Hawaii Islands for the engineer design use or the wave climate study use. This is just one of example of the implementation of the handcast wave, the handcast data set. So this is the last slide. Like, what's the future work? We are thinking to implement the unstructured grid to better resolve the complex nearshore and the bathymetry and the shoreline conditions for Pacific Island in the forecast operation. And we're also thinking to investigate the wave conditions influenced by the mesoscale weather systems such as cold front and its subtropical cyclones. Those mesoscale weather systems are quite complex, and it's usually a challenge for both the atmosphere model and the wave model to better resolve the wave conditions. So we may want to do some research and study in this area. And also in the future, we're also thinking to extend the operational wave forecast to other Pacific islands like Palau, Marshall Island, and Micronesia Island. That's my presentation, and thank you for your attention.
All right, thank you, Ning. Very interesting. And thank you, Justin. Justin, are you still there? Okay, let's open it up for questions now. You can, I'll check the chat box too if you want to ask a question through chat. Okay, go ahead, Roger.
Hi, thank you very much for that very informed discussion on WaveWatch. And we have a lot more of a kind of a practical, I kind of understand the spectrum of how waves are developed. However, by the way, I'm from Guam. If you don't know, I'm the science officer there, and we're required to take a square peg and put it into a round hole. And how I mean by that is when we put out our wave forecast for the area, we have to divide things up between wind waves and primary swell and secondary swell. That's the square hole, and we have a problem with deciding what's a wind wave and what's a swell. And I was trying to look at your one of the graphs that Justin showed way at the beginning that had a comparison of different models with the buoy, and I was trying to figure out, is there any way to determine what a wind wave is versus a swell, versus in the sense of period. And I noticed in the discussion that Ning showed that she called short waves 10 seconds. And in the graph, I think I saw 8 seconds. And out here on Guam, we have an awful lot of 9-second waves. And like I said, we have to assign waves. So we've had a big discussion and no one agrees on. So I'll go real quick question. I don't know what the answer is, but how do you define wind waves? Can it be 9 seconds or less? And how long does it take a wind wave to develop 9 seconds? Because I understand this is all a spectrum over time. And so how do we define that? We also wanted to know if it was okay to assign a wind wave of 1 foot for 5 knots, 2 foot for 10 knots, and 3 foot for 15 knots. Or is that just so way too simple? Is that too much of a question?
Justin, you want to go first?
Sure. So from the perspective from the atmosphere, there's a definition that defines wind seas versus swells. And that's when it's a wave age. So this is the peak celerity of the waves divided by the wind speed. And when that exceeds 1.2, in other words, when the waves are traveling 120% faster than the wind, we would say it's a swell, meaning it can outrun the wind speed. But in your particular location, I would say that you always have constant activity from the east. So I think you could probably tweak that a little bit and just use sources. In other words, you could use waves from the easterly location at, say, that 9-second area, and just always focus on that as the wind sea, because probably your your clients that use that information, they probably are comfortable with knowing that those conditions. So I would maybe just fix it on those easterly events being your wind sea, and then call swells just remote, and maybe not use this atmospheric approach. And the atmospheric approach really is the ocean receiving energy from the atmosphere or not? So if it's less than 1.2, we would say that the behavior of the ocean is still such that it's dominated by energy being received into the ocean. So that's why that definition came to be. So did I address everything?
I think Justin, that's good explanation. But I think from a practical point of view, you will not go to the data and do the calculation. So the reason we use 10 seconds and 14 seconds as the threshold to differentiate wind wave and the swells, we actually discuss a lot on this threshold. Basically, we also talk a lot of local people there. Basically, from trade wind waves generated by trade winds in Hawaii, it's about like basically the waves usually shorter than 10 seconds. And for swells coming from the North Pacific, it can be 14 seconds or much longer. But this is not always. It's just cater to our majority experience. So so we use 10 seconds and 14 seconds. I guess for Guam or other areas, that threshold may be different. Could I say we don't get 14-second waves here. So on an average, just easterly wind day, where it's a combined wind source and swell source of the same trade wind, you could see in the buoy spectrum something like 7 or 8 seconds as a one peak, and then maybe 10 or 11, and that's how we end up breaking it down. Although I don't even know if that's physically logical, because I understand the 120%, but no one's out there calculating speeds over
over time. So like I said, so we divide a standard trade day as a 7-second wind wave and a 11-second swell wave from the same direction. Does that make sense? I don't see 10 seconds very much.
Yeah, it's definitely depends on locations. I agree with that. Yeah.
So what does a 10 knot wind wave, could that create 2-foot seas? Or there's just no way to answer that because it's always time integrated.
Yeah, but I do see for 10 knots trade winds, it's typical trade winds. I think David has a better idea, is about 10 to 20 knots. But for wind wave, we do see 2 foot to 4 foot, this range.
Just with very short periods. Yes.
Yeah.
Yeah, we just never agree on that. And the problem is, there is a problem. The problem is the way that swells go into surf. And the current programs, I think, disregard the short period wind waves and only use swell for the developing surf. So the more we attribute a wind wave, the less we're going to contribute a swell, meaning a less surf. And that's where the practical problem is, because the surf is what causes the rip currents, which causes our danger.
Yeah.
I don't know if that will help you maybe have better way of displaying that information for us between this, either a SWAN model or just maybe practical understanding.
So I think from the forecast point of view, for each forecast plot, at least distributed on the PacIOOS website, we have up to 5 major components. For each components, we didn't exactly say it's wind wave or swells, but we will show the wave height curve, and also the wave period curve and the direction curve. So you can look into those individual wave components and see what's going on inside. I don't know whether that answers your question or not.
Well, I'm not sure either. I know it's very complicated with no set answer, because like I said, it's a spectrum integrated over time. So you can't just answer a question, what does 10 knot wind bring? Because you're going to have to say how long and for how far.
Yeah.
So, okay, I might send you guys an email.
That's good.
Just to ask more clarification. I kind of understood how you were going to give me an answer already. Thank you.
Yep. My experience on the first question is that's really a regional issue. Like in places California or Hawaii, our wind seas are from the local trade winds, and they're less than 9 seconds, and that's easy to differentiate from the long period swell.
Yeah.
But basically it breaks down to like, has the waves reaching you, have they been abandoned by the wind field yet or not? So the swell is stuff that the wind has stopped blowing on it for quite a long time, and it's just reaching you as a gravity wave. Okay, are there any other questions? Anybody? Everybody understood Justin's talk completely? No questions required on any of the terms.
Maybe need to sign up Justin's class.
If you guys have a minute, can I ask a question?
Yeah.
My screen just froze. Was that a yes or a no?
Yeah, sure.
Okay. Just curious about because this pertains to a lot of our students. The large wave events are often from typhoons or tropical cyclones. So how well do the models actually do with those? So I mean, if the model is incorrect, how much of that actually has to do with the weather model being incorrect in terms of the path of the storm or the winds within it, and how much of that actually is in the wave model not being able to deal with that sort of wind field? Or does anybody know?
My own opinion from experience is that if you give the wave model reasonable winds at the appropriate scales, which you need really high resolution to resolve the inner vortex of the model can handle it. And like I mentioned with the input term from Arduin, it works a little bit better for high wind environments because you have that sheltering effect. So the physics start making sense. So my take is that yes, you will underestimate the really peak of the storm, but if you give the model the best wind information and use it at the appropriate scales, you can get a pretty nice match.
All right.
Yeah, for me, and it also depends on the resolution of the wave model, because we have the spatial resolution, we also have the spectrum resolution. So if the resolution is too coarse, then we are not able to model the wave conditions pretty accurate either. And also for forecast, we have another factor. Like, for example, we have to finish the forecast in few hours. We cannot just with a high resolution let the model keep running because that will lose the purpose of forecast. So sometimes we have to trade off between the efficiency and the accuracy. This is a little bit different from research. Operation different from research is based on your computing resources and the time you have to get the best result. And for in terms of hurricane modeling, because the hurricane forecast, the track and the intensity, based on my understanding, it's already a challenge for the atmospheric model. I think with the new GFS source term, it may resolve the forecast better. That will improve our wave forecast too. But for our PacIOOS forecast, we only update once per day. When it's regular weather condition, it's pretty good. But when it's a hurricane condition, because the hurricane keep moving and the hurricane forecast actually is every 3 hours, they will update the forecast. Like yesterday's forecast and today's forecast may not be different, be totally different, but our wave forecast is only provided once per day. So in that sense, that maybe have a larger uncertainty for the forecast result. So when you look at the forecast data, we have to be very careful. Like, yeah, I don't know whether that's answer your question better or not.
Yep, that helps. Yeah, I mean, it's great to know that actually the models can do fairly well with the hurricanes.
Mm-hmm.
Okay, so we're out of time. So I want to say thank you to Justin and Ning. And not only for doing this webinar, but thank you for all your work that you do related to wave models. I really appreciate that personally. It's very important to our participants in our program. And I guess thank you to NCEP for helping with the WAVEWATCH III, and thank you to PacIOOS for your models. They're a great tool for Hawaii and Guam, and hopefully in the future Micronesia, and sorry, American Samoa as well. So I guess, yeah, we'll wrap it up there. So thank you everybody for attending, and I'll post this later on YouTube and get everybody the link to it, so you can review Justin's equations. Okay, thank you.